Good morning.
Good morning, sir.
Good morning, sir.
Okay, so if you have any questions, please ask now before I start. Any questions? Based on our last class means last week, right? Yeah, on last Thursday. Any confusion about the transition state theory? Okay, if it is no, then I will proceed. And whatever I taught up to last class, up to the transition state, the slides are already uploaded in the Moodle. Okay. So today I will finish about the transition state theory, how it will be helpful to understand the mechanism or the nature of the transition state. Then I will teach the Hemont postulate little bit. This is postulate, and after that I will go on about the kinetic isotope effect. That is also very interesting to understand the mechanism. Okay, so I shared the slide. I hope you can see. So this is the slide I showed before last class, that this is a SN1 type of reactions where the carbocation formation of carbocation occurs as an intermediate, and the formation of carbocation occurs in the rate determining step also. So the first things, that how do I understand, how do I determine whether the carbocation is forming in the transition state or not, means transition state in the rate determining step, right? Whether the carbocation is forming in the rate determining step, whether it is or not, how do I know? So first you need to run the kinetics, you need to determine the rate law as I told before. So rate law is showing the rate is equal to K into is a first order with respect to the starting material t-butyl bromide, but it is zero order with respect to water. That indicates that this is a unimolecular reaction, not a bimolecular reaction, because water is not involved. Okay, so maybe the formation of carbocation is happening, but not sure. It is not sure. It cannot tell. Rate law cannot tell whether carbocation is forming in the rate determining step or not. So you have to it is supporting the first step. Okay, so you have to do multiple experiment to establish the mechanism. Okay. So second one, whatever I told last class also, is the measurement of activation parameters, especially the activation of entropy. Entropy of activation is very important. Its value as well as sign will tell you or will give further evidence about the nature of the rate determining step. So as I told that if the disorder or randomness in the rate determining step increases compared to the starting material, then definitely the entropy of activation will increase, right, compared to the starting material. So it will be positive. So in S1 type reactions, you can see here the carbon and bromine bond is getting elongated and being broken, right? So one molecule is now undergoing to formation to form two molecule or two atom or two ion. So it increases its randomness. It increases its entropy. That is the entropy of activation. So if this is the case of the mechanism, then definitely from the Eyring plot, if you determine the entropy of activation, then definitely it will be positive, because the transition state or rate determining step has higher entropy compared to the starting material. That we discussed in the last class. Again, I am recapitulating. Clear? Is it clear or not?
Yes, sir.
Yes, sir.
Yeah, if it is not, please let me know. So if it is the SN2 type of reaction, you can see it's a similar reaction but different mechanism. Okay, so in the SN2 type of reaction, this is a bimolecular reaction. In the rate determining step, two molecules are involved, both molecules. The Br minus, it is attacking on the carbon center, and CCl bond is cleaving. It is happening in the rate determining step, in the first step, not in the second step. And this is a single step reactions. Okay. So if this is the case, definitely you should expect, and this is the fact from the experimental results, that the rate is equal to first, it is the first order with respect to the starting material, that is the ethylene chloride as well as Br minus. So this is a bimolecular reaction. Two molecules are involved in the transition state as it is expected from this kind of transition state. So it also rules out the SN1 type of reactions, that is the formation of carbocation in the transition state or rate determining step. Right? Not only for that, if you determine the entropy of activation from the Eyring plot, so you need to make a plot of K. You need to measure the K at different temperature. That is Eyring plot, right? Ln K by T versus 1 by T. Then what about the del S of activation? You will see it is negative. This is for the supporting. That means in the beginning we have two molecules, but in the transition state it is basically in one molecule, right? So entropy will decrease or increase? It will decrease substantially, significantly. And you can see the value, it is minus 30. Definitely is a good number, is a negative number. Not only for that, its sign is negative. That indicates that whatever the turnover limiting step or transition state or rate determining step, here entropy is decreasing significantly from the starting material. That makes sense, right? Is it fine?
Yes, sir.
Okay, so we stopped here in the last class. So now I'm going to give you the examples, more examples briefly. So this one we the acid catalyzed hydrolysis of ethyl acetate that we discussed before, right? Also we discussed before. So here the rate determining step is the attacking of the water to the carbonyl carbon of the ethyl acetate. So this is the rate determining step. So what is happening? So what will be the value or sign of del S? Here you can see in the beginning water is separate, this is separate, but in the transition state two molecules are coming close to each other and decreasing is entropy. So its value will be negative. Okay, all the examples are given, answers are given here. I think I should omit and ask you, but anyway, you can see the second example, the acid catalyzed ring opening of ethylene oxide in water. This is similar kind of reactions. So first acid will bind H plus. This is specific acid catalyzed reactions. You know that it bind to the oxygen of ethylene oxide and increases its electrophilicity. Then water attack. Here you can see the arrows, right? And ring opening take place. And this is the transition state. So if this is the transition state, what is the sign of del S? Is similar to the first case. It will be negative. It will be negative. Right? It makes sense because two molecules are coming close to each other in the rate determining step. So del S will be negative. So plus or negative sign will give a huge indications what is the nature of the transition state. Okay, two molecules are coming close to each other, they are attacking or not. Okay, any bond length increases or decreases or not. It will give a huge hint to understand what is the nature of the transition state in the rate determining step. Okay. Okay, so the third one you can see is this acid catalyzed hydrolysis of alpha methyl glycopyranoside in water. Okay, this is the hydrolysis. The first step is the H plus will coordinate it. This is a glycoside. Okay, this is the acid catalyzed hydrolysis. So this is the proposed mechanisms. If this is the you can do reverse way. From the sign, you can determine what is going on in the transition state or determining step, or in the opposite way. This is the if this is the proposed transition state or determining step, then you can also predict that what will be the del S of activation. You can see it is very clear. Here I'm just giving the answers to understand you, because you people are the first time learning this. So if this is the mechanism, then what should we expect? What will be the sign of del S? You can see here the oxygen, this arrow, and OMe is cleaving. Here bond is cleaving like an SN1 type of reaction, isn't it? This bond is cleaving. So at the end, what is the next? You will see this molecule and plus OMe. So here this small bond is being broken in the transition state. So you are increasing the entropy in the transition state. So if it is increases, then what will be the del S of activation? It will be positive, right? Is it clear or not?
Yes, sir.
It's very obvious. I'm telling you very slowly. If it is any problem, just let me know. The fourth one is the displacement of iodide from methyl iodide by pyridine. This is a kind of SN2 type of reaction. Okay, this is a kind of SN2 type of reactions. So the pyridine is attacking on the methyl groups and iodide is leaving. Okay, so in the beginning, pyridine is a separate molecule, methyl iodide is a separate molecule, but in the transition state or rate determining step, you can see the rate determining step or rate limiting step. Two molecules are coming close to each other, so it is decreasing its entropy compared to the starting material. So this is always negative, right? What about the fifth one? Fifth one is a kind of, it is an example of SN1 type of reaction. Hydrolysis of T-butyl chloride in water. So this is the rate determining step, where first the carbocation formation occurs in the rate determining step. Carbon Cl bond is being cleaved and form the carbocation. If this is the rate determining step, then what will be the del S? It will be the positive, as we discussed before, right? Because in the beginning one molecule T-butyl chloride, but in the rate determining step the CCl bond is being cleaved, so it is increasing its entropy because it is about to form two ion or two molecule or two atom, right? So it is increasing its randomness, so entropy will increase. You can see it is all, it is the experimental result, whatever the del S value. Okay, del S value. All right, and the sixth one, this is the conjugate addition. So you can see also this is a conjugate addition similar to like SN2 type of reaction. Okay, so here two molecules are also involved in the rate determining step. So the value will be negative. Okay, any questions? Please ask.
No, sir.
Anybody?
Sir, can you repeat why 0 delta S?
Which one?
Fifth one.
It is not 0. It is 10. Okay, I'm going to.
Okay. Yeah.
I actually it's it overlap plus 10. Is clear now?
Yes, sir.
Yeah. It's plus 10. Actually, my red circle overlapped with 1. Yeah. So it's very interesting, right? So how del S will actually, this is a very common experiment to determine the mechanisms, okay? In chemistry and chemical engineering. In chemical engineering, always you will study mechanism, okay? In chemistry, we do a lot of stuffs. And chemical engineering, what is the mechanism, kinetics, everything. If you see any research talks from any chemical engineering people, students or professors, always there are a lot of kinetics, okay? And this is a part of the kinetics. Everything, whatever I'm teaching is a part of the kinetics, not thermodynamics. We are not talking about the energy differences between the starting material and product. We are talking about the barrier. Okay. Anything else?
So, without looking at the rate law, how will you determine between specific acid catalyzed to general? Without looking at rate law?
Tell me again. Sorry, yeah, tell me again.
So without looking at the rate law, how will we determine if it's a specific or generalized rate catalyst?
No, you cannot tell.
We cannot. Okay, okay.
You cannot tell. For mechanism, kinetics is the first things. Okay. Look, let me tell you. I think I didn't tell you in the first class. What is the definition of a mechanism? Maybe I can ask a questions in tutorial or final exam. Okay, what is the definition of a mechanism? Okay, can anyone tell what is the definition of a mechanism? What is mechanism? What is mechanism?
So the proposed path for a reaction.
Proposed path. Okay, but if there is a multiple path, then
Proposed set of paths.
but how can I believe you? There may be 100 proposed path. I can tell you A is B. There is a path A. Okay, path 1, path 2, path 3, path 4. I can tell anything. Suppose in SN1 type of reactions, it can be SN1, it can be SN2. I can also tell a lot of other things. Yeah. So
we can verify via experimental results.
verify. You cannot verify. No one will believe that, okay, this is the mechanism. You cannot verify. That's why I'm asking you, what is the difference in a mechanism? Look.
Sir, accepted path. Accepted by people.
Accepted. No, you cannot tell a accepted path. You cannot. You don't know what is going on actually. Okay. Mechanism, you cannot establish a mechanism. Yeah. Whoever told this is a proposed mechanism, that is more like a scientifically correct. Proposed. You cannot tell this is happening. This is I'm proposing, I guessing. But guess can have a lot of things. So you have to guess with experiment. So definition of a mechanism is that pathway. Suppose A to B, you have 1, 2, 3, 4. There is 4 possible pathway. Okay. So mechanism is that pathway that disproves all other pathway. So you have to do a lot of experiments to disprove. Suppose 2 is your proposed pathway. You cannot establish, okay, this is going on. No one will believe you in science. 8 and B, you cannot tell that, okay, 2 is going on. Okay, this is the 2 is the actual pathway. This is a proposed pathway. Someone told that is correct. Proposed pathway. After you disprove that 1 is incorrect, 3 is wrong and 4 is wrong with experiment. And you should have a experimental support that, okay, 2 is more favorable or consistent with these experiments. So mechanism is that pathway. This is the actual definition that disproves all other possible pathways. Is it clear? You have to disprove. So whenever we are telling SN2, I'm telling the results. Okay, I didn't discuss much because this is the beginner. You are the beginner. Okay, suppose this is an unknown reactions. So there are a lot of other pathway. One of the common pathway is that it can be SN1 type of reaction. But you disproved, we can disprove the SN1 type reactions based on the rate law, because if it is the SN1, then bromine, suppose bromine will be 0 order. Okay, so it supports SN2. You cannot tell with confirmations, but it is disproving that, okay, this is not SN1. Okay, this value and also the sign is also disproving that it is not SN1. It is actually supporting SN2. Is it clear?
Yes, sir.
So mechanism is that pathway that disproves all other pathway. You cannot establish or by confirmation that this is the pathway. This is a proposed pathway. That's why always mechanism is proposed. Proposed. You cannot tell that, okay, this is the pathway. No one will believe. This is a proposed pathway. Now you have to do the experiments to disprove all other pathways. Okay. So what about the experiments? First is the red law. Second one, activation parameters. I'm coming next, another 2 or 3. Okay. So those experiments can help you to disprove all other pathways, and also that can also help you to support your proposed pathway. All right, so this is the second one, activation parameters. Any other questions? Okay, so next one I'm going to tell you very briefly. That is the Hemont postulate. Hemont postulate. Okay, this is not an experimental fact. This is proposed like long time before, more than 100 years before. At that time, there was not much science was developed. I exactly how when I cannot tell. I forgot. Is more than 18th century probably. But this is actually quite useful. Okay, you can see the how useful it is. Okay. So that's what is called Hemont postulate. What is postulate? Postulate is a kind of proposed. Okay, postulate, postulate, theory, hypothesis. So you should understand what are the differences. Okay. So postulate, yeah. What is a postulate? Postulate is kind of hypothesis, right? That is a proposed things, not a theory. Okay, postulate. So what the Hemont postulate tells? Hemont postulate tells, you can see the I wrote it. The activated complex, at that time people didn't know what is transition state, okay, until Eyring proposed. So let's assume this is the transition state, activated complex. The activated complex most resembles the adjacent reactant. Okay, so activated complex most resembles means looks like. What is resemble likes, it's similar, maybe similar in structure. Okay, so activated complex, now you can tell this is a transition state or rate determining transition state of the rate determining step. Suppose a single step, so rate determining step transition state is also in the rate determining step. So the transition state is similar in structure to the adjacent reactant, intermediate if it is multi-step, or product that is closest in energy. Okay, closest state energy. So it is telling that the transition state is have similar structure to the reactant or product, not and or either transition state is similar in structure with either reactant or product or intermediate if it is multi-step reaction, if they are close in energy, very close in energy. Okay, that makes sense. But there is another one term, another condition, as long as the energy differences between the transition state, so that is the transition state or activated state, and the adjacent structure. Adjacent structure means is it adjacent reactant or product or intermediate is not too large. Okay, so what does it mean? So it is telling that, so let's talk about the left hand plot. The transition state is resembled or its structure is similar to the starting material as long as the energy differences of the starting material and to the transition state is not very large, not too large. Okay, not too large. Okay, so you can see that if the starting material and product is very high energy difference, like in the highly exothermic reaction, and if the difference between the starting material, so you can see the energy differences between the transition state and starting material is much shorter compared to the energy differences between the transition state and the product, right? So this is a case of a highly exothermic reaction. Does it make sense? So in a highly exothermic reaction, transition state is always closer in energy with starting material compared to the product. Is it correct? Right? You can see here, highly exothermic. Okay. So if this is the case, then transition state structure is resembled to starting material. That is telling. You don't have to do any experiment. It is just telling. It is an easy to understand what is the nature of the transition state in a special case. If it is a highly endothermic reaction, then definitely whatever the transition state, the energy difference between the transition state and the reactant is much larger compared to the energy differences between the product and starting material. Right? So if this is the case, you should expect, this is obvious, that transition state will looks like the similar to the structure of the product. Because transition state is converting to the product, right? And energy difference is not much. So this is the Hammond postulate. So again, I'm telling that Hammond postulate is telling for an highly exothermic reaction, transition state is closer in energy to the reactant than the product. That means it is also closer in structure to the reactant than the product. So same postulate is telling that in case of exothermic reaction, the transition state is closer in structure to the product than the starting material, just opposite. Okay, so at that time, but it is very helpful actually. Okay, suppose carbon plus oxygen equal to carbon dioxide. What might be is a highly exothermic reactions? What might be the transition state? It might be the existence state of the starting material. It is little tricky for carbon and oxygen equal to carbon dioxide, but it may also tell that okay, carbon and oxygen is probably coming and forming a structure which is resembled to the both atoms. You don't know. Okay, but this is a postulate. It is not an experimental fact, but it is used to understand the nature of the transition state for a couple of reactions in a special case long time before. Okay, but this is used. So, but we are experimental chemists, as I told, that if you want to disprove the all other pathways, you have to do experiment. Hypothesis will not work much. Okay, this is a special case, and this is a hypothesis postulate. Okay, so the next experimental experiment that you will be doing to determine the nature of the transition state or rate determining step is the isotope effect. It's very, very important and very interesting, similar to the activation parameters. Isotope effects. Okay, any questions?
No, sir.
Okay, so let's talk about the isotope effect. Isotope effect will take, I think, 2 classes today and tomorrow. Okay, because it is a little long, and you need to understand actually what is the origin of the isotope effect. There are a lot of equations, but I'm not going to do any equations. I am trying to tell you about the pictorial. I'm trying to teach you about in a pictorial way so that you can understand. Okay, just you can understand that what is the origin of the kinetic isotope effect. How it will be helpful to understand the nature of the transition state. Not only for that, you can also predict from a proposed mechanism that what will be the what type of isotope effect you can expect from there also. Okay, so what is isotope effect? What is isotope? What is isotope? What is isotope?
So elements with same atomic number but different atomic mass.
Okay, good. So elements with same atomic number but different mass. So basically you have different number of neutrons, right? Yeah. So one of the common isotope is hydrogen and deuterium. So you can see the title kinetic. So kinetic isotope effect means what is the effect of on kinetics? What is the effect of isotope on kinetics? Okay, what is the effect of isotopes on kinetics? Kinetics means kinetic barrier, or easily this is the what is the effect of isotopes onto the rate constant. Kinetics is always the first experiment you have to do is the Red law, right? That is the kinetics. So we have the order as well as rate constant. Okay. So in activation parameters, how did you determine the activation parameters? You determine the rate constant at different temperature. So kinetic isotope effect is also the same. In a starting material, something like this starting material, you have two hydrogen here. If you replace the hydrogen with its isotope effect, isotope, that is the deuterium, that is quietly available, right? This is one of the easiest available isotope, that is the deuterium. If you go lab, in my lab, I can show you the deuterium oxide D2O. It is quite cheap also. Okay, so D is the heavier isotope than hydrogen. So we have water in the tap, and in the refrigerator or in our lab we have D2O. So it is, you can easily get the isotopes of hydrogen. Okay, this is the most easiest way to get a isotope of an element, that is the hydrogen and deuterium. Okay. So if you replace this hydrogen, so this is a what is the, this is SN2 type of reaction, right? This is an SN2 type of reaction. This is an SN2 type of reaction. So what is isotope effect? Isotope effect is if you replace this hydrogen, two hydrogen with deuterium, so it will be D and it will be D. Is there any change of rate constant K? Not first step, the overall rate constant. You need to investigate. It may change, may not change. If it is changed, then it will give an hint. Okay, if it doesn't change, then you cannot do it. There is no effect. Okay. If there is no change of K on replacing the hydrogen with deuterium, then there is no kinetic isotope effect. So forget about that. This experiment is not helpful. But in many cases, the rate will change slightly if you replace the H with D. Means you will change the rate constant slightly. Doesn't matter slightly or largely, it may change. If it is changed, then you will have a kinetic isotope effect on those cases, and that how it will be changing from replacing the H or D, what will be the value of K, what will be the sign, what will be the value, that will give you a hint about the nature of the rate determining step. All right. Okay. So this is an SN2 type of reaction. Again, this type of reactions I will tell you in every class. The rate is first order with respect to the both starting material. I told you that del S of activation is negative because two molecules are coming close to each other in the transition state. This is consistent. Now let's see what is the effect of the isotopes on the rate constant. So if it is the H, then it will be the rate constant will be K CH2Cl, MECH2Cl. If you replace the H with D, then it will be MECD2Cl. Now we need to investigate what will be the changes of rate constant, how it compare, the value is same or not. If it is the value is same, there is no kinetic isotope effect. Okay, if the first one is larger than the second K, if the first K for protic substrate is larger than the deuterated substrate, that is the 2, then there will be an effect. Maybe it is the reverse way. So we need to determine what is the value of K by changing the proton to deuterated substrate, proteo substrate to deuterated substrate. Does it make sense?
Yes.
If you have a questions, just tell me. Okay. So kinetic isotope effect. So first thing is that what type of information we may get, you will see, but I'm just telling. So what is the mechanism of a reaction? It will help. It will also tell that is a certain bond, for example here CH Suppose you have CH bond. Okay. Whether the CH bond or certain bond is broken or being broken in the rate determining step. This is being broken. The isotope effect will tell you. The isotope effect, kinetic isotope effect will also tell you what is the transition state geometry. This is also very important. Okay, it can tell, it cannot tell, it can give a hint. It can nothing, no experiment can tell you with confidence, as I told. Okay, it will give you a hint. Okay, that might be the transition state. Kinetic isotope effect may give you a hint about the geometry of the transition state. Okay, it will give a hint. All right. So basically, what is the kinetic isotope effect? As I told, that it is a, just scientifically, it is a minimal perturbations. Do you know perturbation theory in quantum mechanics?
No, sir.
No. Okay, forget about that. Perturbation. Okay, you can tell it's a disturbance. Okay, so minimal perturbations or minimal changes of a reactions by isotopic labeling one of the atoms in the reactant. So as I told before, that if you change H to D, so this is the isotopic labeling. Labeling means you are changing one of the atom to its, if you are replacing one type of atom or element with its isotope, like H is replaced with D. Okay, and how it is disturbing or changing the rate or rate constant, whatever I told. Okay, that is the idea. Okay. It is also very important that isotopic labeling means if you change the H with D, it cannot change the mechanism. It will only slow or make it fast, or maybe there is no effect. So if you do an isotopic change, if you replace with H to D, which has just varying amount of neutrons, but atom is the same because this is isotope, it cannot change the mechanism. It cannot. Only it may change the rate of the equations. It may or may not. If it is may not, then forget about that. This experiment is not useful. But if it is may, then it will give a hint or help you to understand the nature of the transition state. Okay. So, as I told, so one of the common way is that replace the hydrogen with deuterium because deuterium is widely available. You have C12 and C13, but C13 abundance is very, very low. Compared to hydrogen, deuterium is abundant. As I telling, it is quite cheap. Okay, we use it regularly. Also, we have sufficient amount of D2O in our laboratory. That is called heavy water. Actually, yeah, it is heavy. Okay, heavier than water because it has higher mass. Okay, so you can see the starting metal SM, PDT is product. So starting metal is converting and KH is the rate constant. If you replace the hydrogen with deuterium, then it will be KD. So your kinetic isotope effect is very simple. What is the ratio between the KH or KD? You have to determine the rate constant from the rate law. Very simple. Then divide KH by KD, and that is your kinetic isotope effect. If it is 1, means there is no kinetic isotope effect, right? KH equal to KD. So if you replace H with D, there is no effect. So this is not useful to understand the mechanism. Okay. So KH by KD equal to 1 means there is no kinetic isotope effect. Any questions?
Sir, how does it help in the
That I'm
geometry
coming.
prediction?
I take today's class and tomorrow. Okay, I think it might go for the next class also. It is little longer. I will tell you. This is just the beginning. I'm just telling that it is the introduction slide. I think we have another probably like 7, 8, 10 slides probably. Okay, I will tell all details how it will help you to understand the nature of the mechanism. To understand the mechanism or nature of the transition state. Okay, I'm just introducing yourselves with various kind of terms first. Okay, so what is this? How do you determine? So this I'm coming one by one. Okay, but anyway, today I cannot finish. We have only 5 minutes. It will take whole tomorrow, and probably I will continue till Monday. Okay, because it is longer. Okay, I think I will finish within 2 slides. Then I will tell you tomorrow what is the origin, okay, and how it will help. Okay, so now I'm telling you about a couple of definitions, okay, that you need to know first. One is everything is KIE, kinetic isotope effect, but one term is primary. Okay. So one is the PKIE, primary kinetic isotope effect. Okay. Primary kinetic isotope effect, I'm coming in later in details. If any CH or CD bond is broken in the rate determining step, suppose like an E2 elimination, I'm giving an example in the beginning in the introductory slide, that here you can see this CH or CD bond is being broken. Okay. And it's giving ethylene. Okay. So you can see in the transition state, this is the transition state or rate determining step, CH or CD is being broken. If CH or CD is being broken in the rate determining step, then you will whatever the kinetic isotope effect you will get some effect. KH by KD will be different, not 1. Okay, it may be greater than 1 or less than 1, that I will tell later. But those kind of things, this is called primary kinetic isotope effect. Okay, it is broken. There is another one term is secondary. So primary means you can understand this is very important, right? So if CH or CD bond is broken in the rate determining step, so whatever the value of kinetic isotope effect, this will be larger. Okay, I will tell. I'm coming. What will be the value? Next is the secondary, means effect is lower than primary. That's why it is secondary. So secondary isotope effect you will see when the isotope is not directly involved in the rate determining step, or CH or CD bond is not being broken. This is an example of Claisen rearrangement. Do you know Claisen rearrangement from CML 100? Do you remember? No. So here you can see this is a molecule. There are two molecules. One is H, another one is D. Okay, that's what it is showing, H oblique D. There are two molecules. Okay, you can see here what is happening here. Here CC bond is being forming. This is a rearrangement, and this CO bond is being broken. Have you seen? So this bond is being broken and this bond is forming, and this is giving this product. So you are replacing one of the hydrogen here with deuterium. So here CH or CD bond is not broken in the rate determining step. Okay, this is intact. It is not being broken, unlike these reactions, E1, E2 reactions. Okay, so on those cases, you may see KH and KD might be a little bit of different, but whatever the effect or difference, it will be minimal, and that's why this is called secondary kinetic isotope effect. Okay. Now, whatever it is, primary or secondary, those are both are called normal kinetic isotope effect. Normal means if KH by KD is greater than 1, if KH by KD, if K for protic substrate KH, if rate is little faster compared to the deuterated substrate, then definitely KH by KD will be greater than 1, right? It will be greater than 1, and those are called normal kinetic isotope effect. So normal kinetic isotope effect, this is called normal kinetic isotope effect. It is divided into two, as I told in the last slide. One is primary kinetic isotope effect, another one is secondary kinetic isotope effect. In primary kinetic isotope effect, CH or CD bond is broken. I will give you a lot of examples. Just come tomorrow, okay, with also the origin, that what is the origin of these rate differentiations with isotope, that I'll also tell tomorrow. This is a new stuff I will tell you. If CH or CD bond is being broken in the rate determining step, then KH and KD, this value will be little high. It will be greater than 1.5. So KH by KD, if it's 1, means neutral, there is no effect. If it is 1.5 to 6.8, I will come. Why 6.8, not 7.8 or 10? I will come also. Why? I will tell tomorrow. Okay. But if this is more than 1.5, then you can tell, then this is the primary kinetic isotope effect. This is the experimental result. If you see KH by KD is greater than 2, suppose 2 or 3, that indicates that CH or CD bond is being broken in the rate determining step. Okay. If KH by KD is in between 1 and 1.5, that indicates that CH or CD bond is not being broken. But it will also tell what is the nature of the transition state. It can tell. I will tell next. Okay. So here you can see in the normal kinetic isotope effect, KH by KD is always greater than 1. Okay, if it is primary, then value will be little higher, more than 1.5. If it is less than 1.5, then it is called secondary. But KH by KD can be less than 1 also. Those are called inverse kinetic isotope effect. Here KH by KD is less than 1. Less than 1, not negative. Is less than 1. So on those cases, the deuterated substrate, its rate will be faster than the protic substrate. That's why KD will be larger than KH in case of inverse kinetic isotope effect. Okay, on those cases, the KH by KD may be 0.8, 0.9 something, but it is less than 1 because deuterated substrate will undergo the reactions faster compared to the protic one on those cases, and those are called inverse kinetic isotope effect. Is it clear?
Yes, sir.
Okay. So normal into divide into two, primary and kinetic. Another one is the inverse. Okay. Another one is equilibrium isotope effect that I will tell later. Those are not much important. So three kind of isotope effect is very important to understand the mechanism. One is primary, secondary, and inverse. This isotope effect will tell whether the CH or CD bond is broken in the rate determining step or not. Number one. Number two is if it is not broken, what might be the nature of the transition state. It can also tell. Not only for that, this primary kinetic isotope effect also can tell what is the geometry of the transition state, possible transition state, possible geometry. Possible, okay? So that we will discuss tomorrow and probably next Monday. So first, tomorrow I will discuss about the origin of the kinetic isotope effect. The first question will come. This is hydrogen, deuterium, the same element. Atomic number is same. Only one neutron. Deuterium has the only one neutron. Right? How it will affect the rate of the reaction? The first question, right? You may also ask me that why. I understand the KH by KD will different, and depending on the value of KH and KD, it may be greater than 1 or less than 1. But why? So that what is the origin of the kinetic isotope effect, that I will discuss tomorrow at 12 o'clock. All right. So see you tomorrow. If you have any questions, you can ask me. Otherwise, tomorrow.
Sir, in the inverse kinetic isotopic effect,
Yes.
is it always implied that the bond will break, or there will be two cases?
No, it will also tell it will not being broken. Only primary kinetic isotope effect will tell whether the CH or CD bond is broken or not. Okay. So inverse kinetic isotope effect is also a similar kind of secondary kinetic isotope effect, but in the reverse way, inverse.
Okay.
I will also tell when you should expect. You can also, if I give you a mechanism, you can also predict whether if it is the kinetic isotope effect, then it will be the secondary or inverse. You can also predict similar to the activation parameters. Or if you don't know, if I understand the mechanism, then if you determine, then if from the inverse kinetic isotope effect or secondary kinetic isotope effect, we can also support a mechanism and disproved other mechanism. Okay, but primary is quite special. That indicates that CH or CD bond is broken in the determining step. Only this case, primary case. Okay, good questions. But anyway, I will discuss more. Okay. Next. Good. Next question. No? So will I leave?
Thank you, sir.
All right.